So 8.3b on mass and center of mass. Idea. Let our coordinate system be the lamina have this shape. This is y equals to fx. And let's say the density of that lamina is rho. Okay, now here we will talk about a centroid. The word centroid means that's the center of mass of an object with constant density. In other words, the density is uniform at any point of that lamina. Now, so you will see that the mass of this lamina, okay, it's basically the weight of this region here. The weight of this region is equal to, because it's uniform, right? It's the density is constant everywhere on this region, then the mass is equal to the density times the area. If I call this the region D, then that's density times the area of D. That will be rho times integral from A to B fx dx. I think that one is easy to see. Now, the moment with respect to the y-axis, m sub y denotes the moment with respect to y-axis is equal to integral from A to B x fx dx. So imagine if I construct a very little strip here. Let's say that's a little strip here. Okay. Now then, oh, with a rho, multiplied by rho. Okay. Now then, the moment with respect to y-axis is like how much weight of this region here. What is the weight multiplied by the distance from the y-axis? Okay, the mass, I should not call that weight, it's actually the mass. The mass actually rho times fx times dx, right? That's the mass of that rectangle multiplied by the distance from the y-axis. That's what we call the moment. Okay, now the moment of all those rectangles is the integral in this expression. Okay, now please watch the lecture video for the lecture on how I explain that moment. Okay, moment is basically this. If you play jigsaw before, okay, and the mass here multiplied by the length of the arm. Okay, let's call that D1. So the moment is equals to M1 D1. Okay, now you can play jigsaw with somebody else with different weight, with different mass, as long as the moments are the same. So if that person is heavier, okay, with more mass, then the distance has to be shorter. Okay, like Thomas played with his dad when I was really young, when I was a toddler, right? Okay, now I basically sit at the end of the jigsaw and my dad needs to sit very close to the fulcrum. Why? Because my weight at that time just 10 kilograms and my dad's weight at that time was, let's say, 60 kilograms. Okay, so you will see the distance from the fulcrum to Thomas will be 6 times the distance from the fulcrum to my dad, so that we can play evenly, right? Otherwise, if my dad sit at the other end with the same distance I was from the fulcrum, well, Thomas will be basically staying up there, right? Thomas will be up. Thomas will be staying up there. Okay, and cannot go down. However, I jump. Yeah, however I jump, Thomas will be hanging up there. Okay, now what we meant by the moment is again distance times the mass. Now the center of mass on the x-axis is equal to, denoted by x bar, the x component of the center of mass is equals to the moment with respect to y-axis divided by the mass. Now, how about the moment with respect to the x-axis? That's the moment with respect to the x-axis. That's equals to the mass of that rectangle multiplied by the distance of that rectangle from x-axis. The distance of that rectangle, the center of mass of that rectangle from the x-axis is 1/2 y. Okay, that's 1/2 of fx. So the moment with respect to the x-axis is 1/2 rho integral from a to b of fx being squared dx. And therefore, the y component of the centroid is moment with respect to x-axis over the mass. That's it. We are done for this section. Everything else, just putting things together. Hey, let's do problems from our textbook. Would you like to choose a problem from our textbook? Go back up. No, I can see it if you talk about it before I come in. Oh, the graph. Oh, you want to see the graph? Okay. Okay, you good? Okay, any problems you want me to go over from this centroid part here? Okay, if no question, then I randomly pick question then. Let me do number 27. I don't want that to be too easy too. Number 27. Okay, sketch the region bounded by the curve and visually estimate the location of the centroid, then find the coordinates of the centroid. So number 27, we have e to the x. E to the x looks like this. Okay, for y equals to 0, that's the x-axis. X equals 0, that's the y-axis. And then x equals to 1. So x equals to 1. Okay, so we want to find the center of mass of this lamina. Okay, this is y equals to e to the x. I would guess that the center of mass is a little bit to the right of 0.5, a bit to the right of that, because you see, like if at right at 0.5, you see the area on the right hand side is more, right? Okay, so the moment if you hold this region right at 0.5, it will tumble to the right. You see? So we need to hold it slightly to the right, I believe. Okay, so that it balances left and right. Okay, now I will also hold it on the y component. I think I will hold it a little bit to the below 1. If this is 1 here, a little bit below 1, so that it doesn't tumble to the bottom. Okay, that's my estimate. So I think it will be the y bar is less than 1, I think. Okay, and then the x bar will be greater than 0.5. But that's just a guessing though. Okay, guessing approximation, right? Okay, now let's do the computation accurately. Now, first thing we need to do is to find the mass. Okay, first thing we need to do is to find the mass. Oops. So the mass is integral from 0 to 1 rho times fx, which is e to the x dx. Now again, rho is constant here. That's rho times e minus 1. That's the mass. How about the moment with respect to the y-axis? That's 0 to 1, x times rho times e to the x dx. Let me rewrite this first. Rho goes out. X e to the x dx, integration by parts. So that is rho times x e to the x minus e to the x from 0 to 1. That's rho times e minus 0 minus 1. That's just rho, huh? So the x bar will be rho divided by rho times e minus 1. The rho will cancel. That's 1 over e minus 1. Now, E is approximately 2.7, so this is approximately 1 over 1.7, right? So you see it's less than 1 as we expect. Oh, it's actually more than 1/2. That's what I'm about to say. X bar is more than 1/2. That's our estimate earlier, right? To the right of 0.5. Okay, now how about the moment with respect to the x-axis? Moment with respect to x-axis is integral from 0 to 1, 1/2 rho e to the x squared dx. That's rho over 2 integral 0 to 1 e to the 2x dx. The integral of that will be rho over 2 times 1/2 e to the 2x from 0 to 1. That is 1/4 rho e squared minus 1. So my y bar will be 1/4 rho e squared minus 1 over, what is my mass again? Rho e minus 1. That's rho e minus 1. Oh, we can do factoring, huh? The rho cancels, but on the top we get e plus 1, e minus 1 over e minus 1. So the y bar will be 1/4 of e plus 1. That's approximately 3.7 over 4. That's still less than 1, as we expect earlier. Okay, I don't need you to estimate though, by the way. I don't need you to estimate. I just try to show that we get it right. Now, at the end, however, when you write your centroid, you have to write it in coordinate form. X bar, y bar equals to what? Okay, that'll be 1 over e minus 1, comma, e plus 1 over 4.
Hey, Thomas.
Hi.
Hey, we could also just write centroid equals, right?
Yes, that's right. Yeah, you can also write centroid equals to coordinate.
Perfect. Thank
Now,
you.
what if, welcome, what if the curve actually two bounding curve, let's say, for example, number 31. I do odd numbers. I somehow think I did even numbers in my lecture, so I do odd numbers right now. We have y equals to sine x. Sine x looks like this from 0 to pi over 4. Okay, so this is from 0 to pi over 2. That's y equals to sine x. And y equals to cosine x looks like this. X equals to 0. X equals to 0 is here. And x equals to pi over 4. So which region is bounded by this? To be more precise, are we talking about this region or this region? You see what I mean? Is the blue one or the yellow one? The yellow one? Now, is the yellow bounded by x equals to 0 on the left-hand side? No, right? No. Okay, it's actually the blue one. It's actually the blue one. Now, sometimes you really need to sketch that to see which, I mean, it has some ambiguity here. We have to admit. Okay, yeah, there's some ambiguity here. We know that sine x and cosine x intersect at pi over 4, right? But the region that is actually bounded by y equals to cosine x, y equals to sine x, x equals to 0, and x equals to pi over 4 is this region here. Now then, what will the mass be? The mass will be integral from 0 to pi over 4, okay, rho times, now the upper bound minus lower bound. In this region, which function is on the top? The cosine, right? Minus the function at the bottom is the sine. Is it okay? Now, of course, the rho comes out. Cosine x is sine x. Integral sine x is plus cosine x. Is it right? And from 0 to pi over 4. So that would be rho times sine pi over 4 is radical 2 over 2 plus radical 2 over 2 minus sine 0 is 0, cosine 0 is 1. So this is a rho times radical 2 minus 1. That's the mass. How about moment with respect to the y-axis? That's integral from 0 to pi over 4 rho times x times cosine x minus sine x dx. Okay, the rho comes out, right? I will do integration by parts. This one, this is 0. The integral this sine x plus cosine x. The integral of this is negative cosine x plus sine x. So this will be rho times x times sine x plus cosine x minus, becomes plus in this case. No, that's right. That's minus negative cosine x plus sine x. That's from 0 to pi over 4. This is rho times pi over 4 radical 2 over 2 plus radical 2 over 2 minus oh, that's right, that's radical 2 over 2 again. Oh, no. My bad. Yeah, that's for pi over 4, huh? Minus, oh wow, that's multi-layer. Minus when x is 0. So 0 minus negative 1 plus 0. Am I okay? Now on the top, then I will get rho times, that's radical 2 pi over 4 minus radical 2 minus 1. Let's do LCD. Maybe it's helpful So pi over 4. So inside, I will have radical 2 pi minus 4 radical 2 minus 1, which is not really right. I don't think this is right. Did I make any miscomputation somewhere? Negative, oh, negative 4. That's actually make it worse. Because according to what we see here, the x bar is supposed to be positive, right? The x bar is supposed to be, the center of mass supposed to be between 0 to pi over 4. Okay, so there must be some miscomputation here.
The denominator on, shouldn't that be radical 2 pi over 8? Or did you just?
When I add this, I get radical 2.
Oh, got it.
Right? Mm-hmm. Yeah, so let me see my integration by parts. Did I do any mistake with my integration by parts? Here. I make mistake here. I miss a negative here. Oh, I catch you, Thomas. Okay, so it should be just this. It should be just that. So it will be rho times pi radical 2 minus 4 over 4. Right? See, I try to squeeze that negative in there and see what happened. Yeah, yeah, because I try to squeeze that negative in. Not a good idea, Thomas. Well, anyway, then at this point, I can compute my x bar already. My x bar will be, maybe I move it a bit to the left. My x bar is rho over 4 pi radical 2 minus 4 divided by rho radical 2 minus 1. So cancel the pi, I cancel the rho, I get pi radical 2 minus 4 over 4 radical 2 minus 4. Ooh, that's ugly, huh? Okay, now that's for x bar. Let's continue with the moment with respect to the x-axis. That will be integral from 0 to pi over 4 rho times 1/2 rho over 2 the function square. Okay, the top function is cosine squared x. You need to square it, right? Minus sine square x dx. I think what I will do is I take rho over 2 out, and cosine squared x minus sine squared x is cosine 2x dx. It's a lot easier to compute that way. So that's rho over 2 times 1/2 sine 2x from 0 to pi over 4. Okay, then we will get rho over 4. Sine pi over 2 is 1, sine 0 is 0. So then y bar, therefore, equals to rho over 4 big over rho times rho times radical 2 minus 1. So that is 1 over 4 times radical 2 minus 1. That's way too small. You know what? Let's approximate this though. So my x bar, y bar, the centroid is, I would like to compute that to visualize that better. That's 4 square root of 2 minus 1. And how about the other one? Actually minus 4. And this will be pi square root of 2 minus 4 over 4 square root of 2 minus 4. If I use my calculator just to approximate it, what I don't want to happen is that x bar, y bar happens to somewhere here, you know, which is impossible. The center of mass is supposed to be in between, in the blue region, supposed to be, unless you have other type of shape, right? But we can estimate the center of mass is supposed to be somewhere around here, right? Okay, but let's compute it then using our calculator. Pi of radical 2 pi square root of 2 minus 4 divided by 4 divided by radical 2 minus 1. I'm sorry. I think I punched something wrong. Pi square root of 2 minus 4 divided by parentheses 4 times square root 2 minus 4. So I get, this is 0.27 approximately. And .60 approximately, if I round it to 2 decimal places. So approximately 1/4. This is 3/4 divided by, so approximately here. So approximately there. Okay, good. Then it makes sense. That's for number 31. And I'm done with this 8.3. Would you like me to do other problem from this 8.3? Now, if not, then let me jump to 8.5. I plan to go over 8.4, but you know what? I'm a probability person. I do 8.5. Yeah, we are going to do 10.1, but it's kind of like too early to do that right now. Yeah, let's do 8.5. 8.5, don't worry, will not be in your tests. I give you some feeling about this. Okay, now 8.5 probability. Here's the idea. The probability of an event will be associated to the area under the curve of probability curve. We usually call that probability density associated to that event, for that event. It won't be in any of your tests. It won't be in any of your tests. So don't worry about this. I want to show you how interesting, how probability related to what we have so far. And this becomes the one of the big building block if you decide to study actuary in future. Okay. Now probability, total probability is equal to 1, which implies the area under curve is equal to 1. Actuarial work, that's right. Huh? Yeah, this is the very foundation of that. Okay, now let's do number 3. Let's do number 3. They tell us that let fx be 30x squared 1 minus x squared for x between 0 to 1 and equals to 0 otherwise. Okay, so the function basically in this case is being set this way. I don't know what the graph of that function is supposed to look like, but I assume it will look like this. I assume it will look like this. Okay, and the function basically 0 everything everywhere else. Okay, so this is the what the function looks like. Okay, now part A, they ask verify that f is the probability density function. Now f function fx is a PDF, probability density function, if the area under the curve of fx is equals to 0. I'm sorry, equals to 1. The total probability. In this case, of course, then integral from 0 to 1.
Oh, sorry.
Go ahead.
Sorry, what was PDF?
Probability density function. Probability density function. So PDF, if you do statistic, has different meaning. PDF for our file, it's the PDF file, right? Okay, but for probability, that's probability density function. Okay, probability density function. Now, let's confirm that integral from 0 to 1 of 30 x squared 1 minus x squared dx. This should give us 1. So 30 integral 0 to 1 x squared minus x to the 4th dx. This is 30 times 1/3 minus 1/5. Okay, so this is 30 times 2 over 15. Huh? It is not. Hold on. Did I integrate that incorrectly?
Can't you distribute the 30 to the 1/3 and the 1/5 inside? So it's 10 minus 6. Or am I not thinking?
This is still 4.
Oh, right. You're right.
So no, it is not though. Oh, you know what? I copied the question wrong. I'm sorry. I copied the question wrong. I copied this one wrong. The square is outside. Duh. Man, I was like, something not right. So it should be like this. So that's not what it looks like. My bad. Again, I hypothetically call this my fx. Okay. I don't know what the actual shape look like though. Should be x to the 4th. Yeah, maybe something look like that, but I'm not sure. So this is 30x squared times 1 minus 2x plus x squared dx. This is 30 integral from 0 to 1x squared minus 2x cubed plus x to the 4th dx. That's 30 times 1/3 minus 2/4 plus 1/5. So that's 10 minus 15 plus 6. That's equals to 1. Right? No, but because the total area under the curve is 1, so fx is a probability density function. Now, part B. The question is find the probability that the outcome is less than equals to 1/3. Now, so what does it mean? It means if you get this is the curve, right? Okay, let's say that's the curve. I bring it down a little bit so that we can see it better. Let's say that's the curve. Now, the probability of that event, probability that x is less than equals to 1/3, is equal to the area under the curve to the left of 1/3. So the probability for that event is equals to the area for that event. You see what I mean? Okay, so that is equal to the area in that region will be integral from 0 to 1/3 of 30 x squared 1 minus x being squared dx. Okay, so that's 30 integral from 0 to 1/3. Fast forward, that's x squared minus 2x cubed plus x to the 4th dx. So that is 1/81 here minus 1/162 plus 1/, times 243 times 5 times 243. That's the probability. Okay, let me use my calculator to compute that. That is 0.20988. That's if you round it to 5 decimal places. I wonder if you can do this without calculator. Can you do this without calculator? Well, don't worry about it then. Just use calculator. Okay, so that's the probability for that event. And that's it. That's basically it about this section. Okay, now if we want to find the expectation or the average, follow up. The average is basically X bar. Okay, it's basically X bar. Now, what is X bar? As we have learned before, X bar is moment with respect to the y-axis over the mass, right? Okay, now the rho you will see later on will cancel. Okay, the rho will cancel. So rho integral of the domain of x fx dx over rho integral of the domain of fx dx. The rho will cancel. Okay, now the thing is the area of the curve is just 1. You see what I mean? This is a d, not 0. This is a d, the domain of the integration. Okay, so the average for this question will be multiplied by another x. That will be 30 times integral from 0 to 1, x times the fx. Okay, supposed to be divided by 1, no, but divided by 1 will not change the value. Okay, so this is integral from 0 to 1, that's x cubed minus 2x to the 4th plus x to the 5th dx. That will be 30 times 1/4 minus 2/5 plus 1/6. That's 7.5 minus 12, is it right? Plus 5. That's 0.5. Number 6. Number 6, let fx equals to k times 3x minus x squared for 0 to 3. And 0 otherwise. The curve looks like the x-intercept is 0 and 3. Now the thing is we need to find what is k. That's for part A. Find k such that fx is a probability density function. Yeah, basically the integral from 0 to 3 of that fx, k times 3x minus x squared dx has to be 1, right? So this is k times 3 over 2x squared minus 1/3 x cubed from 0 to 3. That has to be 1. So that's 27 over 2 minus 9. That's 13.5. So that's 4.5. So k is equals to 2/9. Now, the probability density function, therefore fx equals to 2/9 times 3x minus x squared on 0 to 3. Then part B, find the probability that x is greater than 1. Greater than 1 means if you have x equals to 1 here, now you need to find the area under the curve for x greater than 1. Now, of course, from this picture we see, we just need to integrate from 1 to 3.
Hey, Thomas, I have a quick question about the last part.
Uh-huh.
So the question was find k so that the function of x is probability density
Function?
function. Does f of x have to equal 1? Or
The area under the curve
it has to equal 1.
has to be equal 1.
So k is the area under the curve in this instance?
No, k is the coefficient. If you take a look on the question, they say that fx is k times something. You need to find what k is that. What
Oh,
is the
so
k?
that the function would be equal to 1.
So that the area under
Oh,
the
area of-
curve
under
is,
the curve,
under
right.
curve is 1.
Okay, thank you.
Okay. Now find the probability that x is greater than 1. That's equals to integral from 1 to 3 of that 2/9 3x minus x squared dx. That's the probability. Okay, so that is equal to 2/9 3/2x squared minus 1/3 x cubed from 1 up to 3. There will be 2/9 times 1, I believe, right? I'm sorry, this is 27/2 minus 9 minus 3/2 minus 1/3. This is 9/2 minus 7/6. Okay, so times 327 minus 7, that's 20, so 10/3, huh? That's 2/9 times 10/3. You see, right? Times 327, 10/6. And 20/6, 10/3. So this will be 20/27. That's the probability. Part C, find the mean. X bar equals to, you just use the actual integral for the probability density function, but you insert x. So x times k times 3x minus x squared dx. You insert x. Okay, I pull the k out, that's 2/9. Okay, integral from 0 to 3 of 3x squared minus x cubed dx. That's x cubed minus 3/4 x to the 4th from 0 to 3. That's 27 minus 81, 243/4. Hold on, something not right here. The average cannot be negative. 1/4. Why 3/4? Who wrote that 3 here? The 2/9. That's 108 minus 81. What will that be? That's 19 plus 8, 27. That's 3/2. That's 1.5, which makes sense. So it's supposed to be 1.5 because if you take a look on this graph, it is actually symmetric with respect to 1.5. You see, if you look at the graph, right? This is the this is quadratic. This is quadratic. Agree? And x-intercept are 0, 0, and 3, 0. We confirm that by computation. Okay, that's for 8.5. If you want to have fun, of course, you can try question like number, I did number 3. So maybe number 4, 5, 6, 7, maybe. Okay, and try to do more if you like. Okay, but again, that's the foundation for actuarial. You need to be really good with your integration and fast. And fast. The reason you need to be fast because when you take the actuarial test, one question basically 3 minutes. One question basically 3 minutes. So if, for example, when you have this function, probability density function, right? Okay, when you have this probability density function, they will not ask you the mean. And even if they do, that's something you should be able to do maybe in 15 seconds. Okay, not by integration anymore. You don't do it by integration, but by realizing, oh, the graph is symmetric with respect to 1.5. So it must be, the mean must be 1.5. The center of mass must be 1.5. You see what I mean? Okay, otherwise, then you won't have enough time for other more important questions, other questions that takes more time. You know. Okay. Now, I would like to take a break right now. I'm sorry. I would like to take a break until 8:30. 8:30, and then we will do 10.1. Okay, let's continue later. Yeah, so we will do parametric curve, which you should have seen in your trigonometry class, but I'm aware that some instructors don't go that far. And I covered parametric curve in my trigonometry class, but I have to admit that I didn't go pretty far. I cover whatever the book covered. Okay, now, but before we dive into the calculus part of parametric curve, I would like you to have a very good instinct about what is a parametric curve. Okay, so I would expect you to watch the lecture. Okay, the lecture is basically the, how to say that, that's the formal teaching for this course. Okay, the one, is it lesson 11 or lesson 12? I forgot. Or maybe lesson 13 already. Week 8A and 8B. So please watch that one. Week 8A and 8B. Okay, please watch. Now, what I will do right now is mainly to provide a better foundation. And I try to follow how I learned it myself before. The way I learned it before, we actually take longer time, a lot of homeworks. So the first thing we will do is we will practice by plotting. So there will be some graphing that you will need to do. Okay, if you have graphing paper, please prepare with you. Okay, and then second, we will learn eliminate the parameter. And then after that, we will learn some important graph and the transformation. Now, our textbook cover briefly the first one and do a little bit part 2, okay? In my opinion, not complete, and also part 3, but not complete. I don't try to offer you something super complete either, but more into building your instinct. Okay, now let's start with plotting. Okay, start first one, practice by plotting. Okay, here's the idea. A parametric curve, is a curve where the x is a function of time, the y also a function of time. Our textbook actually use ft and gt for the x and y respectively. Okay, but I will just stick with x as a function of t, y as a function of t. Now, what happened was in the past, y is the function of x, right? That's what we have before in regular function. Y is a function of x. Now, in parametric curve, both x and y are function of t. Okay, so they are not totally independent, okay, but they are not directly dependent either. You see what I mean? Okay, both of them function of parameter t, and we use t mainly most of the time because it represents time. Okay, now, so for example, we have let x equals to, let's say 2t minus 1 and y equals to t plus 3 for t between 0 and 3. Let's say we have that parametric function. In your calculus 3 later on, we will write it this way. In calculus 3, we will write it as the factor function xy equals to 2t minus 1 for the x component, t plus 3 for the y component, t between 0 to 3. Okay, that's for calculus 3. Calc 3, basically the first couple sections you deal with parametric curve right away. And to have a curve in 3 dimensions, the only way is actually using parametric curve. That's the only way. Now, what I want you to do first is to plot this coordinate by doing the following. We will create a table. Okay, let me do horizontal table. Okay, the t and then the x and then the y. You see what I mean? So when t equals to 0, what's the xy? T equals to 1, what's the xy? T equals to 2, what's the xy? 3 equals to 3, what's the xy? You see what I mean? Now, can you do that for me? Now, once you are done, I would like you to actually sketch the graph by plotting the coordinates. Are you with me? Let's try. Suppose when t equals to 0, the x is -1 and the y is 3. So the coordinate corresponds to that will be -1, 3. When t equals to 1, x is 1, y is 4. The coordinate correspond to that is 1, 4. When t is 2, x is 3, and the y is 5. This is 3, 5. When t is 3, the x is 5, the y is 6. So that's 5, 6. So if I plot this coordinate, x equals to -1, 3, -1, 3. Let's say it's approximately here. So this is when t equals to 0. That's the position of that curve at that time. When t equals to 1, the x is 1, the y is 4. That's when t equals to 1. When t equals to 2, the x is 3, the y is 5. I try to draw it to scale. This is when t equals to 2. And when t equals to 3, the x is 5, the y is 6. Okay, so when time t equals to 0, it's here, then it moves in this direction, it moves to this direction, it moves to this direction, and it stops there. Okay, now suppose I extend that further. Let's say as long as the t is greater equals to 0, then it will give us basically a ray from here and go indefinitely far, right? If there's no restriction on the t, then you will get a line that extends to the left and to the right. Okay, now because the t start from 0, then we say this is the initial point. And if the t ends at 3, we call this the terminal point. Is it okay? Now, let's continue with example 1b. Suppose instead, I say let x equals to 2t minus 1 and y equals to t plus 3. And there's no restriction on the t. How will you graph this? Well, one way is to plot the coordinates, get some feeling on some t's, right? For some t equals 0, 1, 2, 3, t equals to -1, t equals to -2, and so on and so forth. Then you will get a line that looks like basically same to that, but the line looks like this, maybe. Okay, for any t. Now, The second method to get the graph for that is to eliminate parameter. In other words, we express how x and y behave are related in an equation without t. So for example, let's say y equals to t plus 3, right? I solve for t, so t equals to y minus 3. And then I substitute the t in the other equation. X equals to 2t minus 1, x equals to 2 times y minus 3 minus 1, and then simplify. So you will see if we write it in slope-intercept form, then we will get 1/2 x plus 7/2. Okay. Now the graph that we have here is basically that line. Okay, so eliminating parameter is one way to get the graph. Eliminating the parameter is one way to get the graph of that parametric curve. But not every parametric equation can be graphable using this method. To say that you can always do this is misleading. No, it's not. Okay, it's not true. Most of the time it's not instead. Most of the time we cannot eliminate the parameter instead. But for the easy ones, we possibly get it. We possibly do it. Is it okay? Now, the thing is, so we see that line, right? Okay. The thing is when we eliminate the parameter, and end up with an equation in x and y, like the one we have here, be aware that the parametric curve is part of that graph. Maybe, not is. Maybe just part of that graph. Maybe just part of that graph. Now, what I'm trying to say is this. When we eliminate the parameter here, we get y equals to 1/2 x plus 7/2. And when we graph this line, we get this blue line. For this case, this parametric equation here give us exactly this line. Now, the thing is, it is not always true. That is not always true. Okay, let me give you an example where it is not true. Example 1C. let x equals to 2e to the t minus 1 and y is equals to e to the t plus 3. Now, if we solve for e to the t, so e to the t equals to y minus 3, and you substitute that into x, that's 2 times y minus 3 minus 1, you get x equals to 2y minus 7, is right? Okay. Now, the graph of x equals 2y minus 7 looks like what we had earlier. The y-intercept is 3/2. The x-intercept is -7, 0. Okay, so this is the line. This is the line here.
Wouldn't it be 7/2?
Thank you, 7/2. 7/2. 3.5, I mean, yeah. Okay, so this is x equals to 2y minus 7. Okay, however, if you take a look on the parametric equation, notice that what is the minimum value for this? E to the t has to be positive, right? Cannot even be 0. So for any t, you will see your x e to the t will be at least, actually should be greater than 0. So because of that, x must be greater than 2 times 0 minus 1, which is -1. X cannot be less than -1 using this t, using this parametric equation. Okay, likewise for the y has to be greater than 0 plus 3, at least 3. In other words, the equation where we already eliminate the parameter is the one in black color. Yet, when we look back into the parametric equation, it actually starts from here. X should be greater than -1. It's not the whole line. It's not the whole line. It's not the whole line. It's this one. It's just a ray. Okay, it's just a ray. And the initial point is -1,3. Not including -1,3 instead. Now, what I'm trying to say is once you do parametric elimination, eliminate the parameter, then you may get a graph, a curve, which is larger than what that parametric curve is supposed to be. You see what I mean? When I eliminate the parameter, I get the black line, right? While if you look back into the range for the x and the y's, for any t, the range for x and y, that's not all real numbers. You see, it's actually only looks like this. So when we try to graph using eliminating parameter technique, be aware that the graph that you get is greater than, maybe greater than what the graph's supposed to look like. In other words, the parametric curve is only part, maybe just only part of that big equation. Okay, the blue part here, the blue ray here is only part of the black line. And from this example B and C, you also notice that from this example B and C, you notice that we may end up with the same equation in X and Y, okay, but the graphs are not the same. They're similar, but they are not the same, okay? Like you see that 1B, it gives us the whole line, but 1C gives us only a ray. And I can change this easily to something else that it is only a segment. Let's say 1D. If I use this, let X equals to 2 times sine T minus 1, and Y is sine T plus 3. When you eliminate the parameter, you get the same thing. X equals to Y minus 7. Okay, but notice that if you look back here, for any t, your X will be between -3 and -1. I'm sorry, not -3 and -1. 1 and -3, +1. Well, because sine t is at most 1, right? Sine t is between -1 to 1. So when you double it, 2 sine t, the range will be from -2 to 2. Now 2 sine t minus 1 will be between 1 and -3. You see that? Okay, so in other words, even though we get the equation without the parameter, that something looks like this, the one we get earlier. This is X equals to 2Y minus 7. Okay, but the line, the curve here, curve C here, will be only from X equals to -3 to X equals to 1. Only this segment. Only this segment here. So basically, when t equals to 0, it is here. When t equals to pi over 2, it goes here, and then later on come back here, and then go here, and then go to the middle again. It's go back and forth, this segment here. It's like somebody who has nothing else to do is just go back and forth, like that. I mean, even when your t is from -infinity to infinity, even if your t is from -infinity to infinity, the graph you get will be just that segment. Are you with me for now? So be very careful when you do, when you try to graph that by eliminating the parameter. Okay, that's one of the standard procedure though. Okay, don't get me wrong. As if I'm not saying it's wrong. I'm not saying that eliminating the parameter is a wrong method. No, that's not what I'm saying. Most of the time, that's what we do. Okay, but after you get the line, like the curve in this case, the line, okay, then look back into your parametric equation and take heed, pay attention to the range of the X and the T, X and the Y. Okay, now let's do another one, another example, example 2. Now the following is actually known to be a unit circle. X equals to cosine t, y equals to sine t. It is a unit circle because we know that cosine squared t plus sine squared t equals to 1. So x squared plus y squared equals to 1, right? So it is a unit circle. Centered at 0, centered at origin with radius 1. Now, if we try to sketch that, it will be a unit circle. That's not the issue. Okay, but let's take a look on when t equals to 0. When t equals to 0, the coordinate is, when t equals to 0, x is 1, y is 0. So when t equals to 0, it's here. When t equals to pi over 2 is here. When t equals to pi is here. Okay, as you can see, it actually moves in this direction. Now, on the other hand, example 2b, suppose I switch that around. Let C be, the curve C be, have this parametric equation, x equals to sine t, and the y equals to cosine t. Notice that it will also satisfy this situation, right? Sine squared t plus cosine squared t equals to 1, right? X squared plus y squared is equal to 1. It gives us the same graph. That's unit circle, right? But this time, it has different starting point. I mean, different timing, in other words. When t equals to 0, it is not 1, 0 anymore. Okay, when t equals to 0, you are here, it's 0, 1. When t equals to pi over 2, it's here. This is when t equals to pi. In other words, you can come up with the same xy graph even though you have different parametric curve, parametric equation. So example 2 and example 2b has different parametric equation, yet they come up with the same graph on xy plane. Now, so what's the difference? The difference is at different time they have different position. Okay, now in calculus 3, you may have the same graph, okay? Like let's say for example, okay, let's say this is my home and this is my church, okay? And the path to go to my church is, let's say, this way, okay? Now, usually when we go to church, when I go to church, I drive separately from my sister, okay? But we go through the same path. My question to you is, we have the same path, but why we don't have accident? I mean, why I don't bump into her car along the way, even though we have exactly the same path? Now, the reason is because we are at the same time, we are at different position. Okay, the way our satellite being managed to orbit the Earth is they may have intersecting path. But we won't have that accident. Two satellites will not hit each other as long as they are not at the same place at the same time. You see what I mean? As long as they are not on the same place at the same time, right? When this guy is here, then this guy should be somewhere else. Okay, now then how those people in JPL, NASA predict that, you know what, certain comet or certain meteorite, a certain meteor will hit the Earth? Well, because when they compute the parametric equation for that meteor and the parametric equation of the Earth, the path intersecting, and they are in the same place at the same time. Okay, that explains why you go through an intersection. When you go through an intersection, let's say this is the intersection here. Let's say this is the intersection. Okay, and you cross the street this way, and Thomas crossed the street this way. We have intersecting path, but we don't have accident. Well, because we hit this common point intersection of the path at different time. So later on, if you have an accident and you need to give the report, and you blame that person. Well, because that person get to the same place at the same time with me. Okay, because if that person get to the same place at different time, there won't be any accident, right? The reason you have accident is because you hit the same place at the same time. Now avoid that from happening. Okay. Now from this example 2 and example 2b, we learn that we may get the same curve, the XY curve, in this case, both unit circles, even though the parametric curve, the parametric equation are very different. You see? Okay. Now, we can even expand another thing. I hope by telling you all this, your view of parametric curve gets enriched. So what happens if I change that cosine t, instead make it cosine 3t? And this is y equals to sine 3t. Notice that x squared plus y squared is still equals to 1. So they give us the same shape. They give us unit circle. In fact, when t equals to 0, they have the same position, 1, 0. So what is the difference between example 2 here, and let's call this example 2b? I mean 2c. The difference is this. Oh, well, they have the same shape, they have the same initial point, but example 3c is actually 3 times faster. Example 3c is 3 times faster. When the t is pi over 2 for example 2, the position is here. Okay, but when t equals to pi over 2 for example 2c, the position is here. Okay, basically that coefficient makes the point move 3 times faster. Okay, so you still get the same shape, you still get the same initial point, but different speed. Okay. Now, Let's go on with transformation. Let's call this example 2D. Imagine if I multiply the x component by let's say 2 cosine t. So originally cosine t and sine t for x and y, but I multiply by 2. Now what will that be? We can see here this is actually 4 cosine squared t plus 4 sine squared t. That's equals to 4, right? In other words, x squared plus y squared equals to 4. Now that's not a unit circle anymore. That's a circle with radius 2. Now the thing is how to explain that phenomenon. Originally that's a unit circle. Okay, originally that's a unit circle. Okay, with radius 1, now it becomes radius 2. Now, the explanation is here. When you multiply original cosine t by 2, you basically stretch that by a factor of 2 horizontally. If you multiply the y by 2, originally just sine t, you multiply the y by 2, then you stretch that vertically by a factor of 2 also. So when you have unit circle, you stretch it this way, the same way you stretch it this way, then it will still be a circle, but now different radius. It's radius of 2 right now. Now that gives us the idea. Oh, okay, so Thomas, I expect the following happen. So what happened if we extend it differently? Let's say for example 2e, we have let curve C be x equals to 3 cosine t, y equals to 2 sine t. It means we start from a unit circle. Starting from a unit circle, you extend horizontally 3 by factor of 3. Okay, so this 1 unit becomes 3 units, right? You extend that by factor of 3 horizontally. And vertically by factor of 2. Now you will see an ellipse. Okay, in fact, we can show this by equation. We can show this by equation. Notice that x over 3 is cosine t, and y over 2 is sine t. Right? Now cosine squared t plus sine squared t is equal to 1. So x over 3 squared plus y over 2 squared is equal to 1. But this is basically equation of an ellipse centered at origin with major axis along the x by factor of 3 and minor axis along the y-axis by factor of 2. Now, then what happens if we add a constant to x and y? Let's say C is, I will do it algebraically first, okay? x equals to, let's say, -4 plus 3 cosine t, and y equals to, let's say, 1 plus 2 sine t. So from here, 3 cosine t, I add -4. And from 2 sine t, I add 1. Okay, now what will the effect of that be? Now, basically, the x will subtract by 4. You move to the left 4 units. And the y will increase by 1. So the center originally 0, 0. Sorry. The center originally 0, 0. The center originally here. Now you move 4 units to the left and up 1. Now the center will be there. Okay, with the same ellipse. With the same ellipse. Okay, the ellipse will be something looks like this. Hold on. No, it should be look like this. Where this is 3 units to the left, right, and 2 units up, down. Okay, now the center is -4, 1. Okay, so to move the graph, like 4 to the left, you add the x by -4, and to move up 1 unit, you add the y by 1. It's very similar to what we learned before with the regular transformation. But to prove this algebraically, we can do the following. You see that x plus 4 over 3 is equals to cosine t. And y minus 1 over 2 is equals to sine t. Now from algebra 2, we learned that x plus 4 over 3 squared plus y minus 1 over 2 squared equals to 1, right? Cosine squared t plus sine squared t equals to 1. But at the same time, this is an ellipse centered at -4, 1 with major axis along the x stretched horizontally by 3 and minor axis stretched vertically by 2. Okay, so this parametric equation that we learned just now, if you understand the transformation, okay, you can relate that to what you learn in algebra 2 and therefore get the graph. Okay, now one of the important graph is the basic graph in parametric equation, therefore is the unit circle, because from that unit circle, then you will get the larger circle with different radius at different center and an ellipse. Okay. Now let's go on further. Let's go on further. So so far we have learned about lines. So far we have learned about lines and segments and then circles. We have more actually, okay, but instead of spending so much time on other type of graph that don't show up that often anyway, I will go back to our book and talk about work on problems from our textbook. Okay, for example, let's see number 13. I wonder if I did number 12 in my lecture. I do number 12 first. Number 12. We have this curve where x is 1/2 cosine theta and y is 2 sine theta, where theta is from 0 to pi. So notice that cosine theta is 2x, sine theta is y over 2. So cosine squared theta plus sine squared theta, we know supposed to be 1, right? So 2x being squared plus y over 2 being squared equals to 1. That's 4x squared plus y squared over 4 equals to 1. Can you sketch the graph? Well, this is a circle with horizontal extension 1/2, right? And the vertical extension 2. I don't draw it to scale anymore. So the curve is approximately this kind of ellipse. Like that. Okay, that's for number 12. That's what the curve look like. Oh, but I need to slow down a little bit. They say that the theta is from 0 to pi. The theta is from 0 to pi. Okay, so when theta equals to 0, it is here. Pi over 2 here, pi here. So the curve is actually not the whole ellipse, but part of that. Only this part. Okay, not the whole ellipse. So it starts from here. That's when t equals to 0. This is when, I'm sorry, theta equals to 0. This is when theta equals to pi. Okay, and it moves in this direction. It's not the whole ellipse, only part of that. Now, number 13 may be interesting because they mark it in red. The curve is given by x equals to sine t, and the y is equal to cosecant t. Oh, that's 1 over sine t. Right? So from here we see, oh, then y equals to 1 over x. Is it right? Where the t is from, from 0, not including 0, up to pi over 2. Now, what is the graph of y equals to 1 over x? The graph of 1 over x looks like approximately like this. Okay, this is y equals to 1 over x, and this is still part of that. But once we start talking about this restriction here, t is from 0 to pi over 2, right? Then x will be from 0 to 1. You see what I mean? Not including 0 and not including 1. So it will be only this part up to here. In fact, that's an open circle. Let me use this color. Okay, this is when t equals to pi over 2. That's why it doesn't touch that 1,1. Okay, but when t equals to 0, it starts from something very, very, very far up there. Okay, and I cannot even use the arrow here, like pointing in that direction, because if I use arrow like this, it is saying that it goes to that direction, which is not true. We actually come from that direction. It comes from there. Okay, so this is when t is between, not including 0, from 0 to pi over 2, not including pi over 2. So you get the Cartesian equation, okay, but the actual graph of that parametric equation is almost always only part of it. That's for number 13. Are the arrows mandatory or for demonstration? Let me say that it is mandatory so that you see the direction. Okay, at least for your studying purpose, right? When you actually graph that, I don't really care anymore, actually. You know, it's something I assume, put it that way. It's something I assume you know. Okay, but for your learning purpose, it will be better if you put the arrows. Okay, how it moves from the t near 0 to t near pi over 2. And you will see that's what the arrow is supposed to look like. Now, I see number 16 seems to be an interesting question, even though there's a typo there. If you take a look on your number 16, I see this. The curve is given by y equals to square root of t plus 1, y equals to square root of t minus 1. Now, it's not true. This is not correct. It's supposed to be x here, I believe. Okay, now then, how do we eliminate the parameter? So x squared minus 1 equals to t, right? Y squared plus 1 equals to t. So putting them together, x squared minus 1 equals to y squared plus 1. So x squared minus y squared equals to 2, is it right? To make it, this is the graph of hyperbola dividing by 2 that gives us this graph. Let me do it down here. It depends on how good your trigonometry or your algebra 2, actually, to be more precise, the first time you learn it. Okay, but the x-intercepts are radical 2, 0, negative radical 2, 0. And it is a hyperbola that actually opens horizontally. Okay. Now, but if we look back into the parametric equation, notice that the t has to be greater equals to -1 and greater equals to 1, right? Okay. Basically, your x cannot be negative. Your y also cannot be negative, right? Okay. And together, when you look at the domain for t, then you see that the t has to be greater than equals to 1. That's the domain for this parametric equation. Now, but when t is at least 1, okay, then the initial point t equals to 1 is here, right? Square root of 2 comma 0. But y cannot be negative. Y cannot be negative. Therefore, the graph of that parametric curve only go this way. It's from here, go that way. Okay, that's the curve C. Not the whole hyperbola. No, it's not the whole hyperbola. Only that part, only the blue part. Remember in your test 1, number 2, I give you inverse function. I ask you the inverse function and I say pay attention to the domain and range. Okay. The domain and range problems supposed to be something you develop since your pre-calculus class. Now, if you don't pay attention to the need of paying attention to the domain and range, then you may say that the curve is actually the whole parabola, the one I draw in red earlier. But no, it's not true. It's only the blue part. Okay, only the blue part. That's for number 16. How about number 18? Honestly, I don't know this. I look at that question, I don't know what to do. And that's normal. That's normal. Okay, don't be scared. Simply because you don't know how to do it doesn't mean you don't do it at all. Okay, let's take a look. X is tangent squared theta. The y is secant theta. Okay, the theta is from negative pi over 2 to pi over 2. Now we know that tangent squared theta plus 1 is secant squared theta, right? So x plus 1 is equals to y squared. Okay, that's how I eliminate the parameter. So x equals to y squared minus 1. Oh, okay, so the graph should look like x squared minus 1, but we inferred that. Why is the y being squared? Well, because secant squared. Tangent squared plus 1 is secant squared, and the y is secant only, not secant squared. Is it okay? No, that's okay. I don't want you to say sorry for that. That's an honest question. That's an honest question. Now then, oh, your brain, yeah, you don't be sorry. Okay, and I honestly try to go slow because I don't think your instructor in the past actually goes this detail. Okay, I noticed that after teaching this for a while, having the recording from last semester enable us to have more time to dive in, chew on this a bit longer. Okay, now of course I do expect you to know what is the graph of x equals to y squared minus 1. Okay, that's something looks like this. You know what? Let me use red color instead. Yeah, because red color is the graph of the xy equation. Okay, that's x equals to y squared minus 1. But then I need to pay attention to the domain of this theta. Okay, the domain of this theta. Dx is from negative pi over 2 negative pi over 2, so x is positive infinity, but the y is negative, so it actually goes in this direction. It actually goes in this direction. See, this is actually positive infinity for theta equals to pi over 2, right? Okay, but secant theta is what? Hold on. Yeah, negative infinity, right? When theta equals to 0, it's here. When theta equals to 0, it's here. Why I don't feel this is right? No. When theta equals, I feel something not right, but I cannot really tell what's that. Give me a second. I kind of confused myself. When theta is 0, x is 0. Oh, my bad. No. When theta is 0, when theta is 0, x is 0. It's here. Not there. Is it right? It's still wrong. My bad. It should be here. No, just plug it in. When theta equals to 0, then the x will be 0, right? But the y will be 1. So the theta equals to 0 is here. But can I find out what is the code what is the theta for this? I wonder what's that. When the y is negative 1. Is it really the whole curve or only part of that? Any clue? Let's find maybe this one here then. Can you find what theta will be here? What is the theta such that x equals to negative 1 when the y is equals to 0? Never happen, huh? Cannot happen, right? Because x already tangent squared. You see, so it won't be the whole parabola. It won't be the whole parabola. Only part of that. We know for sure this will be part of that. Right?
Could I ask why it's going towards infinity? Or at least going towards the right?
Give me a second. I now realize that I graphed it incorrectly. Oh man, man, I'm so sorry. I am so sorry. What happened with me? I must be really tired also. Okay, the graph does not, it's not like that. The graph looks like this. That's what the graph looked like. Duh. Is it right? So y squared equals to x plus 1. So you move. I must be so tired. I'm sorry, I cannot think that well anymore. I confused myself. Give me a second. Let me a second. I somehow think this is the graph though. When y equals to 0, x will be -1. So that's right. When x is 1, and when y is 1, x is 0. Y is -1, x also. So this is correct. What? I'm sorry. I'm sorry. I'm totally lost. I mean, I'm good. I'm sure this is what the graph look like. Okay, but I cannot detect. I still wonder why I cannot detect theta when theta equals to 0. I'm sure it's there, right? But what happened when theta is negative? Let's say theta is. What the heck? I don't believe this is what the graph look like. Oh, you know what? You know what? I hope you see my confusion. Okay, let me start from this. When theta equals to 0, the x is 0, the y is 1. Is it right? Okay. I keep on thinking that when theta is slightly less than negative, then it's supposed to move in this direction. It turns out that it's not the case. It's not the case. Let's see when theta equals to pi over 4. Where's that? Theta is pi over 4. Then x equals to 1. Y is radical 2. So it's here, approximately. Right? That's equal, theta equals to pi over 4. When theta is pi over 2, then it explodes to infinity. Right? So it's basically like the graph moving this way. Like it's quite slow at the beginning, but it's like that. Now, the thing is, what happened when theta is negative pi over 4? What is your x? Your x is still 1, and your y still radical 2. So this position is the same position with when theta equals to negative pi over 4. To my surprise, the curve is actually moving this way. From negative pi over 2, go to negative pi over 4, go to theta equals to 0, and then it goes back there. As if I'm saying that the curve actually, the actual curve looks like this. It moves this way. Let's say this is the coordinate system. The curve actually moves this way. Okay, so from negative pi over 2, moving along this, going to theta equals to 0, and then going this way back. Do you think it's kind of strange?
I don't really understand this problem, I'll be honest.
Okay, let's go back. Let's go back. I get confused earlier too. I get confused because I really thought that when when theta move in the negative part, then it will go along the red part. It turns out it's not. Okay. What I did is I did plotting. Okay, when theta is pi over 6, what will that be? When theta is pi over 6, x is what? When you square it, you get 1/3. Right? Okay, but what happened to the y? Secant 30 degrees is the reciprocal of cosine 30 degrees. That's 2 over radical 3. Okay, so it's somewhere here. So pi over 4 is here, pi over 6 is here, 0 here. So when x goes from theta equals to 0 to positive, it goes in that direction. See it this way, when theta from 0 to pi over 2, it goes in that direction.
Is this the case because the negative negative opposite values of theta have the same values of x and y? Is that
That's
goes
right.
back?
That's right.
Okay.
That's right. That's right. So when theta is from negative pi over to 0, okay, it actually goes in this direction. So along the same path, it's just go back and forth.
Would that be like it goes back and forth, which is like infinitely, or not necessarily?
No, it's not in, it comes from positive infinity far here anyway, when
Right.
it's negative pi over 2, and then go up to theta equals to 0. And then goes back there for pi over 2.
Oh, because those are the bounds, right?
Mm-hmm. Yeah, I was thinking that it will go eventually touch this point or touch this point, you know, but it turns out that after thinking about that further, that's not the case. Yeah, that's not the case. This one, I'm glad that I actually go for that. It's like if I didn't plot this, I won't see that. I won't see that. See, because if you think about it, negative pi over 6, when theta is negative pi over 6, we'll get the same result here. Okay, so the x and y are symmetric exactly at the same coordinates, right? But at different timing. You know, so yes, it goes from here, negative pi over 2, when theta equals to 0, and then when theta goes back to pi over 2, like that. And at those theta equals to pi over 6, negative pi over 6, plus minus pi over 4, they are exactly at the same coordinate. Okay, this is where I will stop. On Wednesday, we don't have a class, but I plan to be here anyway. And I was thinking to do one problem maybe from your test 2. Your test 2 will be up to 8.3 only. Your test 2 will only up to 8.3. Okay, so don't worry about 8.5. Don't worry about chapter 10. Okay, but on Wednesday, we don't have class, but I plan to be here to answer your questions. Take a look in my old tests. Take a look in my old tests. And you know what? Is it on the 14th? Yeah, your test will be basically on the Wednesday when we come back. Yeah, on the 14th. Your test 2 will be on the 14th Wednesday after we come back. Now, this Wednesday, again, we are not supposed to have a class, but I will be available. And let me just do it this way. What I will do is on the discussion board here, I will post some of my old tests. Okay, let me post it right now before I forget. It's my previous test. So previous test. I think I can show you the one from last semester. Yeah, take a look on that. The one from last semester is fall, huh? Give me a second. I will answer you very soon. From fall 20, Math 262 test 2. And then would you request other semester? I think my spring test is actually the same. So let me go back further. How about fall 19? Do I have 262? Yeah, I have 262. Okay, so at least 2 sets of test 2 are actually posted. Okay, 7.4, 7.5, 7.8, 8.1, 2, 3. Yeah, but 7.5 covers all integration. So you are right. The topics for your test 2 will be from partial fraction decomposition up to up to center of mass, up to the physics. Okay, but we skip the integration by table 7.6 and estimating integral 7.7. Is it okay? That's for today. See you then. So please study from these 2 tests. Okay, please study from these 2 tests. And then on Wednesday, I will do maybe one or maybe both of them. Hopefully only one, maybe only one. Yeah. Okay, but if you have a question, you can ask.